Okay, so here's what we were talking about last time. We were talking about systems of differential equations. Right, they look like this. Sometimes these are called coupled systems. Coupled because of the fact that they're sort of unavoidably connected, right? You might want to call this the y1 equation in which you solve for y1. The problem is y1 also shows up in the other equations. Right? And not only that, but in the what you might want to call the y1 equation, there's more unknown functions than just y1. yn is in the what you might want to call the y1 equation. So these are unavoidably all sort of interconnected with each other, and so again, sometimes called a coupled system. Okay, so we made the observation that with a little bit of sort of notational choices, you can rewrite that system of equations as a matrix equation. And this is much more compact, easier to deal with, and furthermore, gets you sort of more immediately in the sort of the world of linear algebra. You've got a matrix, you've got vectors. It's sort of more naturally set up. Okay. We saw last time, now without proof, but we saw that there is an existence and uniqueness theorem. And again, this is something that we critically rely on, right? And we need to be able to know that when we're looking at an initial value problem, namely one of these kinds of differential equations with an initial condition given, that there is a solution defined, right? And furthermore, that if we have found a solution, that's it, and there aren't other solutions, right? It makes life much more difficult if we don't know this. So this is a tremendous theorem to have on our side. Do note the conditions you need for all of these coefficient functions to be continuous. And likewise, you need for the g on the right-hand side to be continuous. Okay. All right. So now, still at a glance, it looks like we're solving an analysis problem here. We see derivatives, we see functions, we see equations. It looks like a calculus, pumped up calculus kind of a problem. But very last thing we talked about last time was that if you look at it from a certain point of view, it's not a calculus problem, it's a linear algebra problem. Yes, we're looking for solutions to a differential equation, but let's instead think of it as we are looking for vectors in the kernel of a linear transformation acting on a vector space. Right? That's all linear algebra talk, and ultimately it's going to be extremely important to take this point of view, to view this as a linear algebra problem, not as an analysis problem. Okay, all right, so that's where we left off. So picking up from there, the good news continues. And by the way, another quick reminder. So one of the things I mentioned was that, Chapter 6 here, the kind of differential equations we're talking about here, not the same as Chapter 4's differential equations. In Chapter 4, we only had one equation. Nice, right? But it was an nth order equation, and that's unfortunate. Here, it's only first order. That's nice, right? But there's n of these equations. So there's different kinds of complications that we're dealing with in Chapter 6 versus Chapter 4. However, there is an extremely strong analogy. You'll notice a strong analogy as we go through Section 6.1 here, all the various sort of observations that we're going to make and theorems that we're going to state. So you've already seen a couple of them, right? First of all, linear algebra problem. That was one of the big lessons of Chapter 4. Secondly, we have an existence and uniqueness theorem, just like in Chapter 4. Right? And continuing on that pattern, the set of solutions that we're looking for is n-dimensional, just like in Chapter 4. By the way, n being the size of this matrix, so this matrix A here being an n by n matrix, which is equivalent to saying that this y vector has n functions inside of it. Okay. So I'm not going to write down the details of this proof, but I'm going to say it's very analogous to the proof that I showed you of the Chapter 4 result. Now, asterisk, I showed you that proof in Chapter 5. Right? It's very useful to use linear transformations to prove this fact. And so let me just remind you, roughly speaking, how that went. We created a linear transformation T from the vector space of solutions to the vector space of initial conditions which, by the way, don't forget, this is Rn right here. Right? And the idea was, well, okay, fine. We have this linear transform. We have this candidate linear transformation. The formula for this was, roughly speaking, plug in. That's what the linear transformation does. So this function that takes a solution and gives you a corresponding initial condition just by plugging in. Not hard to check that this is a linear transformation. Now that's an exercise that I left for you guys to confirm that this is in fact a linear transformation. Easy chapter 5 problem. And then furthermore, note that the existence and uniqueness theorem tells us that this linear transformation is one-to-one and onto. Bijective, depending on your preference of terms. And because this linear transformation is one-to-one and onto, these two vector spaces have the same dimension. The dimension of Rn, which of course we know is n, is the same as the dimension of this domain, namely the set of solutions that we're trying to understand. So that's how we know the set of solutions is n-dimensional. Okay, so that was the argument that we made in the Chapter 4 context. Morally identical argument goes through here in Chapter 6. I think this is a lovely exercise for you guys to work on your own, or possibly ask about in discussion section. Talk to a classmate, whatever your study group. Come to my office hours. This would be a good one to pound out the details on, but structurally it's just like this, just like it was in Chapter 4, actually Chapter 5, but about Chapter 4. Okay, so we have an n-dimensional vector space. We can talk about a basis for that n-dimensional vector space. A basis is a collection of solutions. Solutions are vector-valued functions, so this is what a basis looks like. And just like we did in Chapter 4, we're going to call this a fundamental set of solutions, or sometimes just a fundamental set. A quick notational heads up. There is a certain kind of a convenience. This might seem a little weird, but to take each one of these basis vectors, and don't forget, each one of these basis vectors, being as it is a solution, right, to the system of equations, the matrix equation, whatever you want to call it is vector valued, right? So it has n different components. And so writing down each one of those as a column and, etc., thus making a matrix, this resulting matrix is kind of a handy notational choice sometimes. So the book calls this a matrix of fundamental solutions. My feeling is that the grammar of that is kind of weird. I'd rather call it a fundamental solution matrix, but whatever. No big deal. And we're going to see pretty shortly why that's useful. For the moment, I'm just going to make the assertion that it's can be a useful thing. Okay. So let's solve one. Right. Now remember, the big idea is this looks like a calculus problem, right? Derivatives, equations, functions, and all that. But we're going to approach this like a linear algebra problem, and we're going to actually solve it ultimately with linear algebra. First, some innocent observations. That is a solution. Now this is plug and chug. This is something you guys can confirm for yourselves. Let me remind you how this works. Don't forget that this system here could be rewritten explicitly as y1, y2. These derivatives are, let's see here, 1y1 minus 3y2, and then minus 2y1 plus 2y2, right? So that matrix equation is the same as this system of first-order equations. And when I say that this vector satisfies that matrix equation, what I mean is that these component functions satisfy these individual equations in the system. Right, so it's just a little bit of calculus, plug and chug, take some derivatives, plug in, do the arithmetic, and lo and behold, it works. Okay, so make sure you can do that. Make sure it's just a good sanity check to make sure that you're clear on exactly what relates to what in what way. Plug it in and make sure that it works out for you. Okay. Okay. So that's a solution. And now here's another plug and chug, easy confirmation. That also a solution. Okay, now, for the moment, I'm not going to talk about where those solutions came from. We'll come back to that in a few minutes. But those are solutions, and at this point, it's all linear algebra. This is a 2x2 system. Theorem tells me that we have a two-dimensional set of solutions. We are looking for a two-dimensional vector space. Forget about solutions. We're looking for a two-dimensional vector space. We have two vectors in this two-dimensional vector space. Not only are these vectors in this two-dimensional vector space, I claim it's pretty clear that these are not multiples of each other. Neither one of these is a multiple of the other. Right? This one here is a scalar e to the 4x times negative 1, 1. So this is pointing in the direction of negative 1, 1. This is pointing in the direction of 3, 2. They're pointing in totally different directions. Right? So we have two vectors, not just two vectors, though. We have two independent vectors in a two-dimensional vector space. That means that they're a basis. That means that they span. That means that the entire vector space that we're looking for is just the span of these two vectors. And so it's over. We are done. And it's just a matter of how we want to write that at this point. You can say, here's a fundamental set of solutions. Right? You can then sort of, if you want to be a little bit more explicit, you can say, therefore, the complete set of solutions is the span of those two solutions, set of all linear combinations. Feel free to write it like that. But notice we're done. Right? Again, where did the magic happen? What really allowed us to solve this problem? It's in the linear algebra. Finding a couple of solutions, that's nice and all, but my gosh, if you don't know the linear algebra, all you're left with is, here's some that work, and I don't know, maybe there's other solutions, I don't know. If I find more solutions, how will I know if there's more beyond that? I don't know. Right? The linear algebra is what answers the question. Yeah.
How did you arrive to those solutions?
Yeah, I pulled them out of a hat at the moment, and so for the moment, I will talk about that later, right? Okay. But for the moment, I want to emphasize the importance of the role that linear algebra is playing. And you asked the extremely reasonable question, right? Of how can I reproduce this on my own? We'll get to that. Yeah. Okay. Okay. Is everybody good? Does everybody see how the linear algebra is what makes this work? Okay. So now I can show you about this whole fundamental matrix business and why we might care about it. Look at this complete set of solutions here. Let me zoom out one notch. This complete set of solutions. And just observe that formula is exactly the same as that. Right? The matrix M has those columns. Right? Multiplying that matrix M by this vector C1, C2. The way you multiply a matrix times a vector is to take the linear combination of the columns using the vector's coordinates as coefficients. You get that. So, very compact, very convenient in a way. Okay. All right. Okay. Hopefully no surprise, but the analogy continues with Chapter 4 in that if you want to find the complete set of solutions to a non-homogeneous equation, such as this one, right, that's non-homogeneous because of this G sitting right here, what did we do in Chapter 4? Well, we stated and proved a theorem about a particular solution and a corresponding set of homogeneous solutions, and how you can just bring them together. Just add the particular solution with your homogeneous solutions, and that gives you your complete set of solutions. And the exact same thing works here in Chapter 6. So you see here, if we have a fundamental set of solutions, and if we have a particular solution, then collection of all homogeneous plus the particular gives you the complete set of solutions to that non-homogeneous equation. It's just particular plus homogeneous, just like in Chapter 4. Okay, now there's two different ways that you can see this, that this theorem is true. One thing you can do is you can write your own little proof of this fact. The way you would do this is you would flip in your notes back to Chapter 4, and you would shamelessly copy and adapt appropriately the proof there in Chapter 4. It's just minor adjustments as needed. These are now vectors, vector-valued solutions, as opposed to just functions, right? But the argument is really, really very much the same. Right? So that'd be one way to do that, and you're welcome to give that a try to prove this theorem. Here's what I think is a better way to see this theorem, and that is to recall that we already have made a general theorem about an all-encompassing category of questions like this one. Specifically, I was talking about this back in Chapter 5, but whenever you have, let me write this as a theorem, if T from V to W is a linear transformation, then, and let me just talk through this because there's a lot to write down. We did this back in Chapter 5. But you can write down, given a linear transformation T, what it would mean to have a homogeneous equation. That would just be T of x equals 0. Right? So there is a corresponding notion of a homogeneous equation. There is a corresponding notion of homogeneous solutions. There is a corresponding notion of a particular solution. And you can state and prove that in this context, whatever your linear transformation is, the complete set of solutions is always particular plus homogeneous, just like it was in Chapter 4. Just like it was in Chapter 1. And so all these theorems look alike because they're all special cases of this one all-encompassing theorem. Right. So to prove the theorem above, again, you don't really have to do a whole separate proof. You just need to realize, and I guess check, that what we have here is in fact a linear transformation. And what we are looking at here is our linear transformation in this case is T of y equals y prime minus ay. So just confirm that this is a linear transformation. By the way, we already did that last time. That's a linear transformation. Previous theorem says that particular plus homogeneous gives us the complete set. How we doing? Everybody on board with that? Okay. Alrighty. Okay. Whoops. There we go. Okay. Wronskian. Again, just like in Chapter 4, right? I mean, it's just, we're going in this pretty much the same order of ideas that we did in Chapter 4. The results are shockingly similar to the way they were in Chapter 4. The Wronskian is going to be a little bit different. Point of view could be taken, and here, let me skip down to the punchline here. Here's what our Wronskian will look like here in Chapter 6. If you're given a list of n vector-valued functions, and if you'd like to know if that list is independent or dependent, you want to have, say, some way to help you figure that out. This is our formula for our Wronskian. It's just the determinant of that fundamental matrix. Now, a common question that students ask here is, why does the Wronskian change? Why is it different? How come there's no derivatives in here like there were back in Chapter 2 when we first saw that other Wronskian? Ultimately, the answer to that question, why is the Wronskian different, is it's a different formula but it's really ultimately the same idea applied to a different context. So I just glossed over a bunch of details. So we're going to go back to the very beginning. I'm going to derive for y'all a generalized Wronskian. This is a very powerful construction. It applies in lots and lots of different areas, uncountable number of different areas, and it's going to give us exactly what we want. Okay, so here's our question. Suppose you have vectors in a vector space. How do you tell if they're independent or dependent? Okay, now before we go on, if this vector space is Rn, we know the answer. Right? That's chapter 1. You have a bunch of vectors in Rn, vectors in Rn. Make a matrix, take the determinant. It answers the question immediately. Right? If these are n times differentiable functions, we have our chapter 2 Wronskian to help us answer that question sometimes. Okay. So notice that this question here, though, is not, we have a collection of vectors in Rn, we have a collection of vectors that are functions of a certain amount of differentiability. This is just, suppose you have vectors in some unspecified vector space, any unspecified vector space, whatever. Then how do you tell if they're independent or dependent? We don't really have tools for that. Right? So here's the idea. This is a wonderfully simple idea. Make a linear transformation. Now you've got a vector space. You can define a linear transformation on that vector space. Now, very importantly, for reasons we'll see in a moment, I need the target of that linear transformation to be Rn. Rn specifically, right? Nothing else, just Rn. Notice, this n is the same as that n. The number of vectors I'm interested in tells me the dimension of the Rn that I need to go into. Okay. All right. Easy chapter 2 result. This being a linear transformation, if the list above were dependent, hypothetically, the images would have to be dependent. Now, again, that's straight up chapter 2. This is an easy proof. Make sure you can do this. The way you do it, that your premise that this list is dependent means that you can write an explicit relation between these vectors. If you write a relation between these vectors, apply T, use linearity, you will conclude an explicit relation between these vectors, thus confirming dependent. Okay, so make sure you can do that, right? Think about how you'd write that down exactly. Okay, but nice result. Let me summarize. If you have a dependent list of inputs, you get a dependent list of outputs. Okay, so now we're going to take the contrapositive of that statement, and I hope you all remember the contrapositive. It's a really neat trick. The contrapositive of P implies Q is not Q implies not P, right? So in this case, if somehow you have an independent list of outputs, you must have had an independent list of inputs. Otherwise, contradiction. Right? So the yellow statement up here is the one that's easy to prove. The green statement is going to be the one that we're going to capitalize on. That's the one that's going to be nice to work with. And here's why. The reason we like this green statement is because these vectors here, they're outputs from T. They live in Rn. Good old Rn, chapter 1. And we already know if you have a list of n vectors in Rn, how do you decide if they're independent? No sweat. Make a matrix, take the determinant. Done. Right? So what we have here is a strategy. It's kind of a sort of two-step strategy that goes like this. Now that we have, whoops. Give me your eraser. There we go. Okay. I claim we've created a construction that behaves like the Wronskian as follows. This thing here that thing. That's our Wronskian-like construction. And notice, if it's not 0, that means that your outputs are independent, and that means that your inputs are independent. That's exactly what our Chapter 2 Wronskian does for us. The Chapter 2 Wronskian was a formula that if it's non-zero, tells you your list was independent. And this is doing the same thing. Everybody on board? Okay. All right. So the beautiful thing about this generalized Wronskian construction is it works for any linear transformation. That is, any linear transformation whose target is Rn. Right, so whatever vector space you're operating in, doesn't matter, any vector space at all. Dream up some linear transformation whose target is Rn, and you've got yourself a Wronskian. Okay, all right, so how did we use this in Chapter 2? Well, now we didn't think of it this way, but in effect, this is what we did. I mean, this was our Wronskian. Where did this come from? Well, you can almost read it off of what we have here. The columns are telling us what our linear transformation is. So our good old Chapter 2 Wronskian is just the result of applying the above generalized Wronskian construction to this linear transformation. Right. Now, why did we use this? What's the point of this linear transformation? Well, again, keep in mind, and this is important, for this whole strategy to work, we need our target to be Rn. I need these columns here to be vectors in Rn so that the thing makes sense, right? So this linear transformation was just one way of taking the objects that I was dealing with at the time that were not vectors in Rn and making vectors in Rn. That's it, right? That's the main reason that this is that this linear transformation is used. It's a linear transformation whose target are in Rn. All right. So here's our new situation. Now, instead of looking at a bunch of functions like we were in Chapter 2, our new challenge is, here in Chapter 6, we're looking at a bunch of vector-valued functions, right? These are more complicated things than the mere functions we were looking at in Chapter 2, real-valued functions. So vector-valued functions. Up here in Chapter 2, we had this way of getting vectors out of what we were dealing with. What we need now is some linear process, some linear transformation that will turn vectors into vectors. Any linear transformation will do that turns vectors into vectors. And so I suggest we use, with the idea in mind of keeping our lives as simple as possible, let's use the easiest possible linear transformation. How about the identity? Let's use it. Just don't do anything. We already have vectors. We're already in Rn. There's no need to do some fancy differentiation stuff like we had to do in Chapter 2. So, applying this linear transformation in this construction gives us this Wronskian. And this is what we're going to use in Chapter 6. That's the Wronskian that works. And there's some other really nice, 2 seconds. There's some other really nice features of this Wronskian. I kind of undersold a little bit that this linear transformation is chosen not exclusively because it's vector valued. There's another really nice thing about this that tragically I don't have time to talk about, but there is something special about it. And likewise, there's corresponding something special and nice about this. We don't need to go into it in Math 216, but this is a particularly convenient, both of these are particularly convenient vector-valued choices in ways that, again, we just don't have time to go into. If you're curious, come talk to me. I would love to expound on this in office hours. Yes, you had a question.
I guess it's not an answer, but does that mean theoretically, you could use a derivative linear transformation for...
Oh, yeah, if you wanted to, yeah. Now, you can't list in different derivatives because then you'd have sort of too many terms. But if you wanted your linear transformation to be just take the derivative of all the components, sure, absolutely. No problem at all. Yeah. And so that gives you a different tool. It's a different kind of a Wronskian. Yeah. Okay. All right. So again, we're going to not have time to go through the details to prove the following result, but we do have a result with this Wronskian, kind of like we did in Chapter 4, that if you are looking not just at a random list of vector-valued functions, but if they are specifically solutions to one of these differential equations, and I really should have written in here, let me do it here, that all of these coefficient functions are continuous. We need for the differential equations to satisfy the conditions of the existence of uniqueness theorem. So we need that to be the case. Oh, and of course we also need A to be n by n. So little additional conditions there. But if your vector-valued functions are all solutions to the same differential equation, then just like in Chapter 4, the Wronskian takes on certain superpowers. The Wronskian is either identically zero and the list is dependent, or the Wronskian is never zero and your list is independent. Those are the only two possibilities. If those conditions up there are met, there is no such thing as a sometimes zero, sometimes non-zero Wronskian. It just isn't. And the independent and dependent break down in the exact same way. Okay, so nice result. Quick example. Looking at the two functions that we pulled out of a hat a few minutes ago. These were those two functions that we confirmed were solutions to that differential equation. There's our Wronskian. Multiply it out, and that Wronskian, you'll notice, is never zero, and therefore this list is independent. Yep.
So like with the first Wronskian we did, like that chapter,
yeah.
Like we're never going to have a situation where the Wronskian tells us nothing.
Oh, I wouldn't say that. I mean, sometimes the Wronskian does tell you nothing. So specifically notice that here there were these big assumptions, right? That these functions were not just random functions off the street, but they're solutions to a differential equation that satisfies, some conditions, right? So that we were working with some nice assumptions there. You do have to be aware that you got to check that, right? You got to make sure that your conditions are satisfied before you just go throwing out results of a theorem, right? So I don't want to tie my hands under what I'm going to ask you. Certainly, I won't be applying this theorem unless it works, right? Right? But I'm not above. I don't know. I haven't thought about what I'm going to put on the test, right? But I mean, to test whether you're checking these conditions, I suppose I might come up with a scenario where the conditions are not satisfied and see who forgets to check. That kind of thing, right? Yeah. Does that make sense?
Yeah.
Yeah. Okay. Anybody else? Yeah, in the back.
Sorry, you did say that there was an additional, it has to be consistent uniqueness.
Yeah, and that's why I put these conditions on here. You need for the coefficient matrix A to be entirely continuous to satisfy. That's the requirement to be able to invoke existence and uniqueness. Yep. Okay. All right. Okay, so that's section 6.1. Moving on to 6.2. So let's actually get our hands dirty. I mean, how do we find actual solutions, right? Again, I pulled these out of a hat several pages back. Once you have these solutions pulled out of a hat, then you get to make your linear algebra arguments and everything just falls in order and, well, we're done. But how did I find those solutions? So that's the next topic to address. In Chapter 4, there were several different cases of homogeneous equations. By the way, we're going to start with homogeneous, just like in Chapter 4, right? Remember, we did homogeneous first. We talked about particular solutions later. There's kind of a different story for particular solutions. Same deal here. There's kind of more to say, though, about the homogeneous solutions in Chapter 6 than there was in Chapter 4. It depends on how you look at it. But we have to break down the homogeneous case into different cases based on this matrix. And specifically, we need to know whether that matrix is diagonalizable or not diagonalizable. Right? So Chapter 5 rears its head. Right? And it turns out to make a huge difference, and you're going to see why momentarily. We're going to start by considering the diagonalizable case. Right? We're going to start by assuming that matrix is diagonalizable. Oh, constant, by the way. Right? I kind of glossed over that part. Constant coefficient means that A matrix is constant. So it being diagonalizable makes something really nice happen, ultimately. Okay, so that's our first consideration. Now, what does diagonalizability bias? We know that if you have a diagonalizable matrix, a change of basis can turn it into a literally diagonal matrix. And diagonal matrices are really great, right? They're very simple. You can do a lot of convenient things with them. So if a change of basis can simplify the matrix, roughly speaking, we're going to ask now, well, can some sort of a change of basis help me actually simplify the system also? Right? And it's not immediately clear. There's kind of slightly different questions. Not immediately clear if you can or can't do that. And it turns out the answer is yes. It works just fine. You just got to be careful with how you write it down. So here's how it breaks down. We've got our system. Y prime equals AY. If A is diagonalizable, then it's a conjugate of a diagonal matrix. Right? So just plug that in. Haven't really done anything yet. Does this system look simpler? No, not really. Right? If anything, it looks a little more complicated. There's 3 matrices where there used to be 1. Seems a little annoying. Right? The slick move at this point is this. We're going to take that P, we're going to multiply by its inverse on the left to effectively, cancel it here and make its inverse appear over there. Right? And kind of a familiar algebraic move. That gives us this. And at this point now, does that equation look simpler? Not clear immediately. Right, it still looks like it'd be hard to solve for y, because there's a bunch of stuff going on here. Now the slick move is to do a substitution. Notice that P inverse y appears twice in the same form. Right? P inverse y prime is equal to d times P inverse y. So since P inverse y is in some sense kind of what we're working with, let's just call it z. Then the whole system rewrites like this. Then you get just z prime equals dz. This is a new system of equations. It's just a good old change of variables, really. It's kind of like a substitution in a calculus problem, right? And now we have a new system of equations, and this new system of equations here is simpler. It's a lot simpler. This is no longer just, if you say, y prime equals ay structurally, I guess it looks the same. But now, this is not just some random matrix. Now this is a diagonal matrix. And the upshot there is tremendous. Being as it is a diagonal matrix, that whole system turns into, let's just write it out. For example, z1 prime is equal to d1 z1. And then now 0 z2 plus 0 z3. I don't have to write that down really because it's zeros. Then I have z2 prime is, 0 z1 plus d2 z, typo, z2 plus 0 z3. I don't really have to write down those zeros. Z3 prime is, 0 z1 plus 0 z2, don't have to write that down, and then plus d3 z3. Notice then my equation simply becomes z1 prime is dz1. Z2 prime is D2Z2. Z3 prime is D3Z3. Couple of really nice things about this. Oh, no pun intended. About this system. This is a bunch of terms went away. That's nice, right? So we got rid of some stuff. Always a win. But more importantly, this is no longer coupled. Right? This system here is completely decoupled. The Z1 equation has only Z1s in it. And Z1s don't appear anywhere else. The Z2 equation has nothing but Z2s in it, and the Z2s don't appear anywhere else, etc. These are now three separate equations, and remember the very first thing we did, first cat out of the box in looking at Chapter 6, is our hope was to say, well, how about we just solve the equations individually one at a time? And then we kind of had to laugh that off as, well, you can't. They're all coupled and sort of interconnected. You just can't solve them one at a time. Now we can. And not only can we, these are easy differential equations. These are all natural growth differential equations. This is all Calc 2 at this point. These are easy. Everybody on board? So this is a fantastic move, right? This idea of diagonalizing the system, right? Taking the original system, rewriting the original coefficient matrix diagonalized, stick that in there, and then you got to move some stuff around and make a substitution, make this choice about z. But the result is mostly from the diagonalization, decoupled system. So here's that system, right? Entirely decoupled, as we discussed. Okay, and it's all over, but the details, we've completely untied the knot, and now we just have to kind of organize the solutions. So I'm going to go through the rest of the details here pretty quickly. And by the way, this little bit here is just kind of a summary, just kind of a reminder of what's happened. This diagonalizing matrix, the P, the thing that allowed us to diagonalize, is made up of the eigenvectors. Just a reminder, right? And that matrix, change of basis, helps us understand a linear transformation by making it diagonal. Analogously, with a system, makes it decoupled. Right? So this diagonalization with eigenvectors idea helps us understand linear transformations. It also helps us understand systems of differential equations. Slightly different details. Okay. All right. So now it's all over, but the shouting. Let's see. Why won't that erase? There we go. Oh, come on. Okay. How do we solve this system? Well, that's Calc 2, right? I mean, this natural growth equation. The solutions to natural growth equations are like this. Right, the solution to z1 prime equals lambda 1 z1 is, well, all multiples of that exponential. Right, Calc 2. Does everybody remember this? I hope. Everybody good? Okay. Solution to the second equation, etc. Solution to the last equation. Keep in mind that these are the components of the actual solution vector, right? These were individual component functions. The solution vector is the vector of those component functions. So we get, suppose we'll erase, come on, here we go. We get that as our z. Now, you, depending on your point of view, you could stop here. You could say, okay, well, this is my z, and then you have to go back and solve for y. Y is equal to pz, right? So you could do that. This is not set up very conveniently, though, for linear algebra. So before we actually do our multiplication back by p, I'm going to rewrite this as a linear combination. Now, this is just a Chapter 1 thing, but our first component being c1 e to the lambda 1x, I can think of just this first component by itself. If I were to pull it out from the rest of the vector, you can think of it as being this. And the E1 vector here is just the recognition that this thing is what goes in the first position. Right? So this is just a linear combinations argument with standard basis vectors. Make sure you can think that through. The coefficients and then these are standard basis vectors. Coordinates are coefficients and a linear combination of standard basis vectors. Okay, right. So now, having written it like this, now notice I have, if I choose to think of it now as such, I have a general linear combination of a bunch of functions that then make up my fundamental set of solutions. Right? So I know that all of my solutions take this form from the calculus above. If all the solutions take this form, well, that means that all the solutions take this form. That means all solutions are linear combinations of these green functions. That's what a fundamental set is. Okay, now, still, these are still z's. Right? We're still talking about the z's. Don't forget, the whole idea of the z's is it was a substitution. It was a sort of a rewrite choice. And I don't really want the z's. What I really want are the y's. Right? So we have to solve for y here. No big deal. Y is just pz. Right? But you do have to actually do that, right? So multiplying by p, take these green z functions, multiply by p, and you get, let's see, oh gosh, I need a different color. You get those are our y's. Everybody on board with that? Now, notice all I did is multiply by p. This line up here is just a reminder that in diagonalizing, P is a matrix that is the change of basis that executes the diagonalization. Its columns are made up of eigenvectors. That's just a reminder. Everybody on board with this? And then a quick result from there. If I can get this to erase. What is PE1, chapter 1 reference? If you're multiplying a matrix times a standard basis vector, you just pick out the corresponding column. So you get that first eigenvector, V1, and etc. Right? The rest of these, you pick out the corresponding eigenvectors. So these are all just those columns of P, namely the eigenvectors of the change of basis matrix. Okay, so this is our final answer right here. This is a fundamental set of solutions to the original differential equation. I guess I don't have the original equation on the board here, but this is the fundamental set of solutions. Okay, so it's there's a bunch of details that are involved in the process, but fundamentally what we're talking about here is decouple with a diagonalization. Once you've decoupled and done your change of basis, well, now it's just a little bit of calculus and then some rewriting. All the rest of this stuff is just rewriting the solutions to get back to a convenient way to represent the actual solutions that I'm interested in. And here's the really tremendously good news. This process, if your matrix is diagonalizable, this process always goes through exactly the same way. Right? So I like to present this as a calculation, but actually without kind of realizing it, we have done far more than just a calculation. We've actually just done a proof. What we just did is proved that for any diagonalizable matrix A, the corresponding system, these are the solutions. These lambdas are just the eigenvalues. These vectors are just the eigenvectors. It's always the same argument. You always get the same result. And so we have this theorem. Always the same every time. So really nice result. If your matrix is diagonalizable, that matrix has eigenvalues. It has eigenvectors. Put your eigenvalues there. Put your eigenvectors there. And that's your fundamental set of solutions. And now, I've shown you two things then. I've shown you, on the one hand, I've showed you this theorem that you can just plug into. I've also showed you the diagonalization argument that proves this theorem. And I want to emphasize, both are important. Now, day in and day out, if you find yourself looking at a diagonalizable system, yeah, plug in, right? You don't have to go through the diagonalization process every time. Just plug in, for crying out loud. Absolutely, right? But do keep in mind that this class is not just about plugging in and getting answers, right? This class is also about ideas and seeing, how processes work. So test questions very reasonably might be, I want to see a diagonalization, right? I want to make sure that you understand the process that leads up to this result. So make sure that you know the argument, the calculation that we did that yielded this result, but also make sure, for just practical convenience, that you are really good at doing the result as well. And a trivial example right here gives us the results we were looking at last time. So I pulled the rabbit out of a hat with that first system. Oh, come on. There was our system. The matrix you recognize, we know the eigenvalues and eigenvectors. And that theorem then gives us that fundamental set. So that's where the rabbit out of a hat came from. Immediate application of this diagonalization theorem. See y'all later. Have a good Wednesday.